Energy is prosperity. We know that. Energy is prosperity. Energy makes things. Energy moves things. Energy grows our food and prepares our food. Energy keeps our homes warm in the winter. Energy keeps our homes cold in the summer. When we think of prosperity, we usually think of the OECD world. That's what we think of as prosperity. But the real story of prosperity over the last 50 years has been the growth of the non-OECD world and it moving into prosperity. If you define the global middle class as people who can spend something, say, between $10 and $100 a day, the global middle class has grown from about 1 billion people in 1975 to 4 billion people today. It's added 1 billion people in the last 10 years. Fundamentally, what does it mean to join the middle class? It means moving from a mindset of minimizing risk to a mindset of maximizing opportunity. It means the freedom to dream. It means the freedom from the constant crushing fear of not having enough. It means being able to dream. Now, you still have worries, of course. It doesn't mean you're free from worry. We still worry about how we're going to pay the mortgage and make the car payment, but they're fundamentally different worries than the worries that you have when you live in poverty. Since most of us grew up in at least the middle class, it's difficult for us to think about what it means to make that transition. The move towards prosperity is one of the most profound transformations the planet has ever seen. Maybe one of the most striking examples of this growth is China. Now, China is an interesting and an unusual case for lots and lots of reasons, but it's instructive. In 1975, essentially no one in China lived in the middle class. Today, 60% of China lives in the middle class. In 1975, life expectancy in China was 60. Today, life expectancy in China is 80. In 1975, about 2% of the Chinese population went to college. Today, 60% of the Chinese population goes to college. Energy is prosperity. In just 2000, China produced about half as much electricity as the United States does. Today, China produces 2.5 times the amount of energy that the United States does, more than the United States and Europe combined. Today, China has 40 nuclear power plants under construction. Last year, China announced the new dam that would be built in Tibet that would be 3 times the size of the Three Gorges Dam, already the largest dam in the world. Energy is prosperity. We achieve prosperity by producing energy. It's critical that that energy be zero carbon. The link between energy use and prosperity is remarkable. It's an incredibly straight line. It's straight. This is a log-log plot. It's a straight over 3 orders of magnitude. And importantly, you notice that there are no countries that are in the high income, low energy use quadrant of this plot. There is no way to prosperity without energy. And that trend persists if you look at individual countries over time. But if energy is prosperity, then today prosperity means emissions. 80% of all our energy comes from burning fossil fuels, with the remainder from nuclear and renewables, mostly hydro. 60% of our electricity comes from burning fossil fuels. And it's worse than just burning fossil fuels to get the energy that induces prosperity. Prosperity itself induces a set of behaviors that produce more emissions in a sort of self-reinforcing passion. So as we achieve prosperity, we build infrastructure. We build infrastructure out of steel and cement that together are responsible for 15% of emissions. As we rise in prosperity, we eat more calories, and especially we eat more beef that is again responsible for 15% of emissions. As we rise in prosperity, we want mobility. We travel more. And we travel in vehicles that are powered by gasoline and produce more emissions. 80% of the planet has never been on an airplane. So we need to do this. We need to achieve prosperity in a way that doesn't produce emissions. So how much does it cost to decarbonize? How much does it cost to decarbonize? And more importantly, how much are people willing to pay? It's not hard to do these things. We can decarbonize. The question is, how much does it cost and how much are people willing to pay? Well, there's a couple ways to think about how much it costs to decarbonize. The first, that was popularized by Bill Gates, is the idea of a green premium. And a green premium then is just what's the difference in the cost between a business as usual solution and a carbon-free alternative. And I can write it as a percentage as well. So this is good for thinking about how individuals are going to make decisions about decarbonization, a green premium. Another way of thinking about what it costs to decarbonize is the idea of a marginal abatement cost. And a marginal abatement cost is just the cost of a zero greenhouse gas product versus the cost of a business as usual product per ton of carbon avoided. So that's the marginal abatement cost per ton of carbon avoided, and then I can plot the cost of producing a carbon-free good or service per ton of carbon against the total number of tons of carbon, and I get a marginal abatement cost curve. The integral under this marginal abatement cost curve is what it costs to decarbonize the entire economy. Okay, so green premium, good for thinking about how individuals are going to make decisions. Marginal abatement cost and marginal abatement cost curves, good for thinking about how much it costs to decarbonize an entire economy. So thinking about what it costs is one half of the equation. The other half of the equation is, what are people willing to pay? What are people willing to pay to decarbonize? Well, if you go and ask people, and there's been a couple of very prominent surveys that were done in this regard, what you discover is about 80% of people in the OECD world say, yes, I would absolutely pay something extra to decarbonize our economy. And then you say, well, how much? And you discover that on average, people say, I'd pay about 10% extra. All right, well, that's good. But then it turns out that that's a little bit different from the reality, because the next thing you discover is only about 20% of people actually believe that their individual behaviors have an impact on the global picture. So, you know, yes, I get it that cars are bad, but me driving to school instead of walking to school, that, you know, it's such a small, it doesn't, so people don't believe that their actions contribute. And second of all, when you get around to looking at what people will actually pay, you discover it's more like less than 5%. So what we discover when we go and look is people say, yeah, I do something, but really not so much. And that's in the OECD world. That's in the OECD world. If we go to the developing and emerging world, it's a completely different story. Once you realize what it is to live in poverty, once you realize what it means to make that transition from living in poverty to living in the middle class, you know that nobody's going to wait. Nobody's going to put that off. Prosperity is going to win out over emissions every single time. Put another way, when what you're trying to do is put food in your kids' mouths and a roof over your head, you really don't care what might happen to the environment 200 years from now. So there you go. As unsatisfying as it might seem, what's the acceptable green premium? What green premium are people going to pay? They're going to pay nothing. Okay? So $0 and 0 cents is the acceptable green premium. So if we're going to find a way to decarbonize things, that's what we can afford to spend. Now there's another important piece of this that we need to keep in the back of our minds as we're chugging along here. And that is, as societies rise from poverty to the middle class, they build out an infrastructure. They build out a giant infrastructure, a massively interconnected infrastructure that has a lifetime of decades, maybe even longer. And because it's so interconnected, it's incredibly difficult to replace. If you build out the infrastructure that we have today in the OECD world, you're going to get the same thing that we have in the OECD world, right? Now, there's lots of reasons that electrification of transportation has been slow in the OECD world, and especially in North America. But part of that reason is because we built out a massive infrastructure for using gasoline-powered cars. It's critical that as we develop these zero green premium solutions, we deploy them in the developing and emerging world before they build out an infrastructure that's difficult to replace. Okay, so we can't pay anything, but what does it cost? So what does it cost? We said that the integral under that marginal abatement cost curve is what it costs to decarbonize an entire economy. So what does it cost? Well, that's a little tricky. So it turns out that a number of people have developed these marginal abatement cost curves on different occasions, and what you discover is they're all over the place. So here we have two different reports that were done by two very credible groups, and we discovered that in 15 years we went backwards? No, that can't be right. And the problem is that you have to make all sorts of decisions as you're making these marginal abatement cost curves about what technologies might work, what technologies might. There's a million little decisions that go into this, and it has the effect of putting your thumb on the scale. And so while the idea of a marginal abatement cost curve is pretty straightforward and it's easy to think about, the problem is that as a practical matter, not so good. But we're at just the right moment in time, because today we have available to us artificial intelligence and large language models. And so there's probably a way now to build these marginal abatement cost curves without us working on it, without us doing it, okay? And so that's exactly what we decided to do. We said, let's go ahead and use AI, use LLMs to make marginal abatement cost curves. Well, so this is quite the adventure. So we worked with Ben Haley and Ryan Jones at Evolved Energy on this project. We could spend a whole hour talking about exactly how we did this. We don't want to do that. It's really pretty straightforward. So what we use is a set of agents, usually 3, to figure out the cost of decarbonizing a particular sector. And then we use a 4th agent to compare those answers, check them, and avoid hallucination. You can see right away that there's a ton of interesting opportunities here. We can do Monte Carlo analysis and see how varying the inputs a little bit changes things. We can do these things regionally. We can do these things over time. There's all sorts of interesting things that we can do. How we do it is pretty straightforward, at least conceptually. So we use a linear cost optimization model that represents technologies as activities that transform inputs into products and services. And then it allocates technologies and activities and flows to satisfy global energy needs. And it consistently tracks upstream energy use, energy services, or energy use, costs, and emissions. So for each technology then, the model constructs a levelized cost of output. What's it going to cost to produce 1 unit of output? And the model combines capital cost and OpEx to yield the marginal cost of producing 1 unit of the technology's output. And now then, decarbonization occurs by just substitution. Okay, so all I do now is I change the technology into a carbon-free approach. Multiple approaches that produce the same product generate blends, like electricity, gasoline, things like that. And because the entire system is solved simultaneously under a least cost objective, upstream, downstream, all adds up. So it's a pretty straightforward thing to do from a conceptual perspective, difficult to do in practice, and we will, over time, tell you a lot more about how we did that. But what we really care about here is the bottom line. So we go ahead and we do this. We use AI to generate marginal abatement cost curves and ask the question, what is it going to cost to decarbonize the entire economy? And the answer, you have to make a few assumptions about how carbon capture is going to work, but the answer is about $7.5 trillion. What does it cost to decarbonize the entire economy? About $7.5 trillion. Now that seems like a lot of money until you remember that the global GDP is about $120 trillion. So it's actually only about 5% of global GDP. But whatever, we said we're not going to pay green premium. Nobody's going to pay a green premium, so it doesn't really matter. So what to do? What to do? Well, in 2015 at the COP in Paris, the Breakthrough Energy Coalition was announced as a private sector counterpart to the public sector mission innovation. Shortly after that, we announced the formation of Breakthrough Energy Ventures, funded by a subset of the Breakthrough Energy Coalition. It was created in the sort of smoking crater of Clean Tech 1.0, where something between $25 and $50 billion went up in smoke, trying to map the tech model of investing onto the very different problem of clean tech. It was built from the premise that we needed very deep technical expertise to evaluate these technologies. BEV's mandate then is to support the development of technologies that can mitigate at least 0.5 gigaton per year of CO2 equivalent GHG emissions and at zero green premium. Today, of course, we're investing out of our 3rd flagship fund, Breakthrough Energy Ventures 3. We have a follow-on fund, Select, for some of our technically de-risked companies, and we also now have a fund devoted specifically to sustainable aviation fuel done in collaboration with the One World Airlines. We've been at this for about 10 years now, And so it's kind of instructive to say, well, how are we making out? How are we making out? What progress are we making towards dealing with that $7.5 trillion problem? Why don't we take the technologies that have been developed by the 130 companies that we've invested in over those 10 years and put them into 3 big buckets. The first bucket are technologies that have a negative green premium. A negative green premium. It saves you money to use the carbon-free alternative. So just make money. Doesn't matter what you believe about global warming. The second big bucket are technologies that have a green premium that's pretty close to zero. That's basically zero. So doesn't really matter. One's carbon-free, one's not. And then the third bucket are technologies that still have a green premium, but where that green premium is falling, and we think someday it might get to zero. So let's think about what might go in those buckets. Let's think about first the technologies with a negative green premium. The obvious way you get a negative green premium is efficiency solutions, right? Efficiency solutions that are going to save money. So let's think about examples of that from our portfolio. Luxwall develops windows that have the insulating capacity of walls. Just stop and think about that for a moment. Have the insulating capacity of walls. Today we've replaced incandescent lights with LED lights, so most losses, energy losses from your house, from residential buildings, are through windows. It's energy that leaks out through the window. So something like 60% of all the energy loss in your home is probably through a window. We have building standards for the insulating capacity of a wall. Most building standards say the wall has to have an R value of 16. No building standards, at least in most jurisdictions, for how much energy you can lose through your windows. So how are we going to make energy efficient windows? Well, we have double pane windows. We can put argon and things like that between the windows, and that turns an R value of 1, which is effectively no insulating capacity of a single pane of glass, into maybe an R value of 2. But we know vacuum insulated glass is a really, really, really good insulator. We've known that for a very long time. Think about the thermos, right? Everybody's got a thermos. We've used that. We know vacuum makes a really good insulator. The problem with making windows that have vacuum as an insulator is that it's really hard to manufacture them. How are you going to take 2 panes of glass and pull a vacuum between those? The genius at one of our portfolio companies, Luxwall, was figuring out how to manufacture those windows. And they do it essentially by putting a series on a grid of little plastic spindles that hold 2 pieces of glass about 1/16 of an inch apart, and then pull a vacuum and seal that hole. The real genius of this, or at least a real genius of this, is the thickness of that glass, that double pane glass, is the same as a single pane window, which means if I want to do a retrofit in a building, I don't have to swap out the frames. I can just swap out the glass. Today, Luxwall is producing windows in its first factory in Michigan and is actually building a second factory in Detroit, Michigan. So moving along well. And we have other companies in our portfolio that are doing this. AeroSeal that seals not just ductwork but whole houses. Blue Frontier that uses liquid desiccants to avoid vapor compression cycles in air conditioning, on and on and on. So we have a number of companies that have negative green premiums through efficiency. But it's not just efficiency. There are other solutions in our portfolio that also offer a negative green premium. There are about 1 billion cows on Earth. There are about 1 billion cows on Earth. Cows eat lignocellulose, which is an incredibly difficult material to digest. Cows digest that lignocellulose by populating their gut with a family of organisms that break that lignocellulose down into volatile fatty acids that are absorbed then from the bovine gut. The problem with that approach from the perspective of the cow is that this also produces an enormous amount of hydrogen, a gas that is problematic for the cow. And so the way the cow deals with that is it colonizes its gut with another family of microorganisms, a family of archaea, that take that hydrogen and turn it into methane. And that massively reduces by about 5-fold the volume of gas. So that's good, except that methane is an incredibly powerful greenhouse gas. And so cows are responsible for about 15% of global emission. And again, that number is growing as the planet rises in prosperity. Well, one of our portfolio companies, a company called Ruminate, feeds these cows small amounts of bromoform, a chemical that's found in algae that inhibits the formation of that methane, and you can eliminate as much as 100% of the methane from the cows. Now, you would think, well, that's great if I've got cows that are living on a feedlot or dairy cattle that have to come in to be milked a couple of times a day, but cows that are living on a pasture, how do I get the drug to them? And it turns out that there are delayed release formulations, or I can put it in the water that I set out there for the cows to drink. So that's great, right? That's great. Inhibits the production of methane. Except that if I'm a farmer, why the hell do I want to use this? What's in this for me, right? It just costs me money to feed the cows bromoform. Except that it turns out that when I stop the production of methane, I actually increase the productivity of the cattle. And so in dairy cattle, you discover that if you inhibit the formation of methane, some of those calories are directed back into the cow, and the cows increase their milk production by as much as 10%. So there's the motivation for me as a farmer. I don't care about methane, but I increase the production I increase my yield by as much as 10%. So there are approaches, there are technologies in our portfolio that have a negative, negative green premium that are not just efficiency. Okay, how about that second bucket? Technologies that have something close to a zero green premium. One of the toughest sectors that there is to go after is the steel and cement that we use to build infrastructure. Steel and cement together are responsible for about 15% of greenhouse gases. Cement in particular, about 8% of global emissions, and incredibly difficult to abate. We use it at unbelievable scales, almost literally incomprehensible scales, and the stuff costs $100 a ton delivered to your front door. So where's the margin that you're going to use to try and beat the carbon out of this? Well, let's think about how we make cement. Cement is effectively calcium oxide. We generate calcium oxide by mining calcium carbonate out of the ground and then putting it into a rotary kiln and heating it up to above 1,000 degrees Celsius to 1,400 degrees Celsius, and that does a chemical conversion, turning calcium carbonate into calcium oxide and releasing CO2. This is what a rotary kiln looks like. I generate enormous amounts of CO2. Between the amount of CO2 that I generate in the chemical reaction and the CO2 that I generate burning the fuel to get it that hot, I make almost as much CO2 as cement. The production of a ton of cement generates somewhere between half a ton and a ton of CO2, depending on what it is that you're burning. Hugely problematic. So how am I going to deal with that? Well, one thing that I could do would be to change that kiln so that I captured the CO2 that came out of the kiln. And lots of people have tried to do that, but it's nowhere near as efficient, and it provides quite a significant green premium. So that's not going to work. But there are other sources of calcium oxide, calcium silicates. You can mine that out of other rocks. And in particular, you can mine it out of hard rocks like basalt. One of our portfolio companies does exactly that. They dig basalt out of the ground, a hard rock, and then they extract calcium oxide from the basalt. And they don't have to burn anything, and they don't do a chemical reaction to generate the CO2. But the concentration of calcium in basalt is much, much, much lower. It's about 3 times lower in basalt than it is in calcium carbonate. And so the math doesn't work, and it's hard rock. But you get all sorts of other things out of that basalt that I can valorize. And in particular, I get the starting material that makes aluminum. I get titanium. I get magnesium. I get valuable metals that come out of this rock. At the same time, I get the calcium oxide. And valorizing those co-products gives me a zero green premium. Now, eventually, you're going to saturate the market for things like aluminum and magnesium. But those are enormous markets, and it'll take a very long time to saturate that. Well, what else can we do to get the green premium on cement down? You notice there's another material that they dig out of here as well that I've got labeled as SCM. SCM stands for supplementary cementitious material. SCMs are materials that will participate in a cement-forming reaction. So when I make the cement wet and let it harden, they'll participate in that chemical reaction that makes cement, but they have no cementitious properties on their own. If I take an SCM, put it in water, it just makes a mess and nothing ever happens. SCMs traditionally have been things like blast furnace slag and coal ash, and they're aluminum salts and things like that. The problem, of course, is that they're not very good SCMs. I can replace maybe 20% of my cement with these SCMs, and hopefully, as we burn less coal and things like that, there's fewer and fewer of them around. So we need new SCMs. We need different SCMs. One of our portfolio companies, a company called Terra CO2, is mining aluminum silicates and then converting those to the right size, shape, and morphology to act as very effective SCMs. Terra CO2 is now building its first plant in Dallas, Texas. Another of our portfolio companies, a company called Ecosem in Ireland, has been making and selling SCMs for a long time, traditional SCMs. More recently, though, they have been developing the pioneering work of John Vanderlei, a professor in Brazil, to make particles that are the right size and shape to pack very effectively. So these eco-cements are controlled size particles that again allow you to massively reduce the amount of cement that you use because they pack so efficiently. So between the Terra CO2 SCMs and the EcoSem's particle control size, I can replace probably more than 50% of the cement that I had to put in there in the first place. And then finally, as cement hardens, as the concrete hardens, it naturally absorbs CO2 out of the atmosphere. It carbonates the cement. But if you're making cement, as you harden that top layer, you stop how far into the cement the CO2 can penetrate. So another of our companies, a company called CarbonCure, carbonates the cement as it's being poured. And that allows you to reduce the total amount of cement that you need by on the order of 10%. Okay, so now add it all up. I've got brimstone, where I can make cement that is exactly the same as the ordinary Portland cement you buy or make any other way, but that produces no carbon, okay, at least until I saturate these other byproduct markets. I then use SCMs and control the particle size, and that allows me to reduce the amount of OPC that I need by on the order of 50%, and then I use CarbonCure and allow it to reduce another 10%. And so together, if you add all these things up, what I get is cement that is exactly the same as traditional conventional cement, except that it produces no CO2 and with zero green premium. All right, well, what about that third bucket? That bucket where we still have a green premium, but where the green premium is coming down. And a lot of those fall into the broad category of electricity. Electricity production is growing enormously. We saw an example of that already. Remember that one of the best ways there is to decarbonize is to electrify everything and then decarbonize electricity. So we need a way to produce massive amounts of zero carbon electricity. Well, how can we do that? We've got three sources of zero carbon electricity that are available to us. There's the electricity that arrives as solar energy from the sun in the form of solar, wind, and hydro. So that's one approach that we can use. We have the energy that's contained in the earth as heat that we can extract as geothermal. And we have nuclear energy. So where are we on all of those? Well, we know today that intermittent wind and solar is some of the cheapest power there is on Earth. Both of them are between $20 and $70 a megawatt hour, and in some geographies and configurations, even less than that. It's some of the cheapest energy that there is on Earth. But there's a number of challenges with it. First of all, it's intermittent. You don't get it all the time. You get it when the sun shines and when the wind blows. And that's not what I want to run a grid. That's not what I want to do things. I want firm power. If I have to add storage to firm that power, that adds cost. I get solar energy, I get wind energy where that resource is, not necessarily near where people need it. So I have to build a solar farm where there's sun, where there's land, where I can do it. That means I have to move the energy. Transmission is hugely problematic, both permitting new corridors and just the total amount of electricity that I can move down that transmission. Congestion, all of those things together, storage, transmission, congestion, more than double the cost of that electricity. So can we reduce the cost of those things so that I can reduce the cost of zero carbon electricity? Well, we have a couple of our portfolio companies that are working on transmission that allow you to move larger amounts of electricity to where the electricity is needed as opposed to where it's generated. One of our portfolio companies, a company called TS Conductor, uses a carbon filament strengthening fiber inside of a traditional transmission cable. And that allows you to put a lot more power down a line. what happens on a normal transmission line is I start to put more and more power down it, that line heats up. As it heats up, it sags. And as it sags, it eventually touches vegetation and starts fires. So what TS conductor does is add a carbon fiber in that, and that stops that sag and allows you to put 3 times as much power down an existing transmission corridor. And then, of course, I can move very large amounts of electricity if I have superconducting materials to deliver that power. China now has 40,000 kilometers of HVDC superconducting cable. The normal way that we make superconducting cables is with high temperature superconductors. High temperature here means liquid nitrogen temperatures, but they use a lot of liquid nitrogen, and that liquid nitrogen is expensive. And so one of our portfolio companies, a company called Veer Energy, uses the latent rather than sensible heat enthalpy of liquid nitrogen, and that reduces the amount of liquid nitrogen that I need by about 10-fold. We mentioned storage as a challenge for using intermittent wind and solar energy. We also know, too, that I can avoid that storage today is dominated mostly by lithium iron phosphate, and especially Chinese lithium iron phosphate. That is great for short duration storage. Remember, there's an inverse relationship between the length of time I have to store energy and what I can afford to pay for that storage. By the time I get to weeks or months of storage to deal with long intermittency periods, lithium iron phosphate has no cost entitlement to those domains at all anymore. Rather, you need battery chemistries, things like iron air, and that's what Form Energy, another portfolio company, has developed. And Form today is building and shipping their batteries out of an 800-person facility that they built in West Virginia. So a number of opportunities from our portfolio that allow us to deploy a lot more intermittent wind and solar energy. The second big bucket that we talked about was geothermal energy. Geothermal energy today is about 1% of global energy, about 20% of that for electricity and the rest for heat. Traditionally, to do geothermal energy, you need 3 things. You need heat that's close to the surface, you need water to extract that heat, and you need porosity to enable good thermal conduct between water and the rock. Those 3 requirements mean that geothermal energy is limited to a fairly restricted set of geographies on Earth, mostly a few places around the geysers in California and some geographies like Iceland. But today, modern drilling technology allows us to massively expand the range that I can deploy geothermal. First of all, as I go down, it gets hotter. If I go down 4 kilometers, I can find geothermal pretty much everywhere west of the Mississippi in the United States. So I massively expand the range. If I can go down 7 kilometers, I can get geothermal energy anywhere on Earth. And now I can also take advantage of drilling technologies that were developed for oil and gas and add laterals, very long, kilometers long laterals that allow me to massively expand the range of rock over which I can extract that energy. And then through fracking, I can induce that porosity that I need. So I can generate the conditions that I need to create geothermal and massively expand the range of geothermal that's available. In fact, the IEA has suggested that perhaps as much as 35% of global electricity could be generated by advanced geothermal energy. Well, one of our portfolio companies, Fervo Energy, is today in southwest Utah developing what will be the world's largest advanced geothermal facility, the Cape Fear project. The project now is fully permitted. The electricity is fully contracted. When it is complete, it will be 500 megawatts in size. Today, they're completing the first 100 megawatts of that, and that will be online later this year. On the subsurface side, the bores are mostly drilled at this point. Record-setting cross-flow tests have been completed, demonstrating the viability of the reaction, and that part is coming along well. On the top, the equipment is being installed. The buildings are up, the pads are poured, the Rankine cycle turbines that will produce the power are being installed. Importantly, a pilot facility that Fervo brought online in November of 2023 is still producing power today without any thermal drop-off, and that's a problem that has plagued conventional geothermal resources. Advanced geothermal is a real thing. Advanced geothermal is a real thing. It will bring zero carbon power in a cost-competitive fashion to the world. And then we have nuclear energy. We said that nuclear fission today produces about 10% of global electricity. So the way that nuclear energy works is I convert very small amounts of mass into energy according to Einstein's famous E equals mc squared formula. In nuclear fission, what I do is I take a heavy nucleus and break it into two lighter nuclei, where the sum of the mass of the two light nuclei is just a little bit less than the mass of the heavier nucleus that I started with. Nuclear fission today is responsible for about 10% of global electricity. That number has been constant or falling slightly from the late 1970s, effectively from the time of 3 Mile Island. After the 3 Mile Island accident, the cost of nuclear fission rose more than fourfold. Those cost increases reflected the hazards, the challenges of dealing with nuclear fission. And those are really threefold. The first is the products of nuclear fission are radioactive and remain radioactive for millennia. They have to be stored for very, very, very long times. The second is the product of nuclear fission are fissile and can be weaponized. And the third is that nuclear fission is inherently a chain reaction and so always susceptible to a runaway reaction. Now, there are a number of new reactor configurations that are coming online today that try to minimize those problems. TerraPower, that Bill has been involved with for a very long time, is a great example of that family of reactors. But these problems are really challenging and they're really difficult to deal with. Nuclear fusion, on the other side, avoids many of those problems. So in nuclear fusion, what I do is I take two light nuclei, fuse them together into a heavier nucleus, where the mass of the heavier nucleus is just a little bit less than the sum of the mass of the two light nuclei that I started with. Nuclear fusion avoids many of those fundamental challenges with nuclear fission. The products of nuclear fusion are radioactive only for decades, so they still have to be stored, but not for the time periods or anything like the time periods. The products of nuclear fusion are not fissile and can't be weaponized, and this is not a chain reaction, and so I don't have to worry about runaway reactions. But the big challenge I have with nuclear fusion is how am I going to get two nuclei together? When I start with atoms, I have a field of electrons around those nuclei that stop the nuclei from approaching each other. So what I have to do is somehow overcome those enormous repulsive forces of atoms. One way that I can do that is to heat the whole thing up. And if I heat it up hot enough, I strip the electrons away from the nuclei and create a plasma of electrons and nuclei, and now the nuclei can come close to each other. Well, the problem with that is that happens at temperatures equivalent to those that you find at the core of the sun. And so I can't contain this in any sort of a physical vessel. So what am I going to contain it in? Well, I can contain it in a magnetic field. I have charged particles, so I can contain it in a magnetic field so it doesn't touch anything. So-called magnetic confinement fusion is by far the farthest along on the path to nuclear fusion. And in fact, one of our portfolio companies, Commonwealth Fusion, is by far the leader in this space. Commonwealth Fusion is building at Tokamak, the donut-shaped ring that we will contain the plasma in to do nuclear fusion. It's built on these magnet segments that you see being installed that were created from a new class of high-temperature superconducting magnetic materials. In Devens, Massachusetts, this tokamak is now well along. It's close to completion, and it'll be started probably next year, probably in 2027. It's quite far along. And already, Commonwealth Fusion Systems has announced an agreement with Dominion Virginia Power to build their first commercial site, a 400-megawatt facility at the James River site. Magnetic confinement fusion is far along at this point. And it's not just tokamaks if we're thinking about magnetic confinement fusion. There is another shape of a magnetic confinement device, a so-called tokamak, that limits field instabilities. Another one of our portfolio companies, a company called Type 1, is far along on the construction of this class of device, and that too will come on before too long. And not just magnetic confinement fusion, so-called Z-pinch fusions, a company called ZAP. We have a company called Examer that uses laser technology that was developed for SDI to do inertial confinement fusion, on and on and on. The old joke about fusion is that nuclear fusion is 30 years away and it always will be. It's just not true anymore. Practical nuclear fusion devices, especially magnetic confinement, at least initially, are much closer to market than they have ever been in the past. And then we have a number of technologies that help us with new areas that will be important in the 5 broad areas that we invest in. One of those really interesting areas is access to space. Space is perhaps closer today as a frontier for exploitation than it ever has been in the past. There's all sorts of interesting things that you can do there. So for instance, we don't have day and night in space. The sun shines all the time in space if I want to collect energy there. I can either beam that energy back to Earth, or I could use it to do compute in space. There are other bodies in space that I perhaps could mine to exploit minerals. And so, of course, NASA's OSIRIS-REx mission visited an asteroid, collected materials, and brought it back to Earth. The huge challenge with exploiting space is the cost of putting material in space. In the 1980s, at the time the space shuttle flew, it cost about $50,000 to put a kilogram of material in space. That cost has dropped enormously over the past couple of decades, now to about $1,000 a kilogram, mostly through the activity of SpaceX. The critical advance in SpaceX was the reusability of the first stage of the rocket. And that allows you to massively reduce the cost of space launch. And SpaceX now has flown their first stage over 30 times. But it's difficult to get below $1,000 a kilogram unless you have a reusable second stage. And to do the kinds of things that we'd like to do, we have to get well below $1,000 a kilogram, more like $100 a kilogram or a couple of $100 a kilogram. And today, as you heard just recently, we have one of our portfolio companies, Stoke, that is doing just exactly that. Now, reusing a second stage is an awful lot harder than reusing a first stage. When that second stage re-enters the Earth, it's traveling 17,500 kilometers an hour, and all of that energy has to be scrubbed off as heat. The genius of Stoke is using hydrogen as a fuel for the second stage, and then using a fraction of that hydrogen as a coolant. So because hydrogen has a very large enthalpy of vaporization, it makes a really effective coolant. Okay, so how does this all add up? Let's go back to this marginal abatement cost curve that we looked at before. We said, how much does it cost to decarbonize the entire economy? $7.5 trillion. Now we have this big collection of technologies that are getting close to or are already at a zero or even negative green premium. So imagine I had a magic wand. Imagine I had a magic wand that I could wave and magically swap out existing infrastructure for the products and technologies that we talked about today that have a zero green premium. What fraction of this green premium would I address? And the result is really extraordinary. The answer is we could get rid of something like 40% of all emissions. 40% of all emissions if you deployed the technologies that we have now at or near a zero green premium. Now, before we get too carried away here, remember, I've been incredibly optimistic. I don't have a magic wand. I can't magically swap infrastructure out. There's infrastructure that's deployed that has a lifetime of decades. Nobody's going to tear that out and put it in the garbage, but we could do that. I've also been optimistic on what we can achieve in cost targets and things like that. But look, even if I could do only half of it, it's extraordinary what we've accomplished. So let's just stop and think about this. Breakthrough Energy starts 10 years ago. In aggregate now, we've raised a little more than $4 billion. We've deployed about $2.5 billion and invested in 130 different companies. Over that same period of time, all of Clean Tech 2.0 has invested about 10 times that, about $180 billion, something like that. And over the same period of time, all of venture has deployed about $2.5 trillion. $2.5 trillion. And if you hold your mouth just right, you can see your way clear to displacing something like 40% of emissions. And we haven't even tried. We haven't even tried. Imagine if we tried what we could actually accomplish. We need to stop arguing about global warming. We need to stop shaming about global warming. We need to recognize that energy is prosperity. And today, 80% of our energy is carbon-based. And that prosperity will win the argument over environmental damage every single time. We need to redouble our efforts to develop and deploy these zero green premium solutions that provide business as usual product, not something that's kind of the same or almost as good, business as usual products. No extra cost, no emissions. We need to work doubly hard at deploying these technologies in the developing and emerging world, where they will have an outsized importance, where I don't have to tear up existing infrastructure. We need to work hard and work together to build a prosperous and sustainable world. Thank you very much.